Okay, hello all you crazy people out there. My name is Michael. I like wizards and dragons and making games, and it is time to start doing 3D collisions again. So the last time I left off with this project, we had 3D collisions between various shapes and between triangle meshes. They did not perform very well. I'm going to take a wild guess that most of you want your games to run faster than 17 FPS with a single collision detection between a tree and a block. So in the next couple of videos, we are going to do a little bit of work on the various data structures that represent these collision shapes, and we're going to make this run a little better. As always, standard disclaimer applies. This is part of a long-running series on 3D collisions in GameMaker that I've been working on for the better part of a year now. I highly recommend watching that series from the beginning before taking on this video if you have not already. So this video is not going to include a few things, but I do want to get to at least most of them in the future. One, as I mentioned, we're not actually going to be checking for collisions against 3D meshes today. Today we're just going to be setting up the data structure. Also, and I have a few friends who would be very upset with me if I didn't at least mention this, there are other ways that you can structure this data to accelerate 3D collisions, but today we're just going to be covering octrees. Also, I'm not going to be dealing with things like translation in space or rotation in space with these triangle meshes, at least not yet. Strictly speaking, that's been the case for all of the 3D collision shapes that I've done so far, but since these triangle meshes are loaded from a file in this case, they're not even created at a certain point in the room. It's especially... At least I suspect it'll be an especially glaring omission in this video. Definitely we'll get to that eventually. I would consider that to be a pretty important thing to cover. So firstly, I'm going to go and delete all of this code, all of this for loop code, because I don't want to run it by accident and suddenly have the game giving me like single-digit frame rates. Mesh and ray and line. Okay, and I'll make the font size bigger. So I'm not going to be getting back to any collision detection code in this video. What I am going to do in this video is I'm going to set up the data structure, which is going to enable us to cut down on the amount of work that we have to do. There's a few different strategies for doing this that people have employed over the years, but the one that we are going to talk about today is the octree. So as I'm sure most of you already know, the octree is the lesser-known cousin of one of the earlier grunt-type enemies from The Legend of Zelda, and by using them we can... Okay, fine. Octrees are a kind of spatial partition, which subdivide a 3D triangle mesh into pieces. For a visual representation, I'm showing on screen right now a similar data structure known as a quad tree. These types of data structures subdivide triangle meshes into essentially halves, and they sort the triangles in the triangle mesh into one or more of the subdivisions. And this allows you, when you're doing collision checks, to only check for collisions with triangles that are in a particular region. Quad trees subdivide a mesh into four, quadrants. Upper left, upper right, lower right. And if you did the same thing in 3 dimensions, an octree, as the name implies, separates the space into 8 sections. I don't know if there is a, 3D equivalent of the word quadrant. Octant just sounds wrong.
Hey.
And you can do this recursively. You can subdivide each quadrant of a quad tree into its own quad tree. Or in 3 dimensions, as you're going to see in this video, you can subdivide one section of an octree into its own inner octree. I was considering making general computer science videos on recursion and on runtime analysis before I did this one, but then I decided that I put this off for long enough. I don't want to put it off even longer. Maybe another time. So that is what we're going to be doing here today. We are going to be creating an octree based on an array of triangles. So the first thing we're going to need to do to set this up is we are going to need to be able to get the bounding box of a triangle mesh, of a triangle array. That's going to involve figuring out the minimum and maximum points of every triangle in the triangle array. And we can do that. We can initialize a few variables. I'm going to say var bounds min is going to be a new vector 3. I'm going to initialize this to a few values. Let's say infinity, and infinity. It may sound weird to initialize the minimum bounds of an object to infinity, but when we compare each further point in the triangle array to the minimum bounds, anything is going to be less than infinity, so that makes infinity a good default value. Likewise, var bounds max is going to be a new vector 3. This is going to be negative infinity, and negative infinity on all three axes. So to get the minimum and maximum of the bounds of a triangle array, triangle mesh, I'm going to be using those two words interchangeably. I hope nobody minds. we can simply loop over the triangle array. So for var I equals 0, I is less than array length. This is probably a good time to remind everybody that I will not be writing 100% optimal code here. This for I equals 0, I is less than array length could be written in a slightly more performant manner. But I'm going to be writing what I hope is readable code here. There are definitely things that you can do, GML optimizations that you can use to speed things up, but those are not going to be included today. It might be another future video topic, come to think of it. So for every triangle in the array, I can say try is going to equal triangle array index 0. And to update and to check the bounds of the triangle, we can simply say bounds min.x is going to be the minimum of what's already there. Bounds min.x try dot the first vertex dot x try dot the second vertex dot x try the third vertex dot x. And we can do the same for y and z. This is going to be very copy and pasty for the first couple minutes. Bounds min.y is going to be the minimum of the existing y and y of all 3 of the points on the triangle. And bounds max .xyz is going to be the maximum of bounds max .x triangle vertex a .x triangle vertex b .x and so on. So this is going to be very plug and play, as I said. I'm going to assign a new value, and this is going to be the collision mesh's self.bounds is going to be making use of one of the helper functions that I wrote a very, very long time ago now. New collision axis align bounding box from min max. We already have the min, and we already have the max. This is going to create an axis align bounding box from these minimum and maximum values, as opposed to creating one from a position and a half extent, the way that the actual call app constructor would. So before I do anything else, I'm going to just insert a little bit of code. And I don't want any of you to particularly worry about this. This is just going to be a little visualization that I'm going to add to the draw event of the call test mesh object. If you want to make use of this debug draw method for anything yourself, you're more than welcome to. It literally constructs a wireframe based on the edges of a cube, and it draws them with the align list. It draws them as a line list. It's just not particularly relevant to the video at hand, and I don't want anyone to look at that and spend a great deal of time getting hung up on it because they don't know what it's doing.
Hey.
So getting back to a collision mesh. The bounding box is just there to help us out. The actual collision structure for the octree, I'm going to go and create myself a new script. I'm going to call this call underscore octree. Really? GameMaker. Alright, there's a weird, at least in the version that I'm using, I don't know if they fixed it in future releases, but there's a weird issue where GameMaker will, like, randomly open the folder that a resource lives in if you hit a certain hotkey. It's very strange. Anyway, let's see, I'm going to call this call octree node. Actually, no, I'll just call it call octree. This is going to be a constructor. The constructor for this octree is going to take 2 parameters. One is going to be the bounds, and one is going to be the mesh. The bounds are the bounding box that defines the bounds of the octree, and the mesh is just a reference to the object that the octree is part of. So in our case, this call mesh. So let's just assign these to local variables, to instance variables rather. Self.bounds equals bounds. Self.mesh equals mesh. 2 other things I'm going to define. One is going to be self.triangles. This is going to be an empty array for now. We will populate that later. And self.children, child is going to be initialized to undefined for now. So this is the constructor for an octree. It will not do anything very interesting for now, but now that we have now that we have the constructor added, I will go back to the collision mesh and say self.accelerator is going to be a new call octree. The bounds are going to be self.bounds. This is the bounding box of the mesh as a whole, and the mesh that we are going to pass is going to be obviously just ourselves. Next, let's assign something to the triangles array inside the octree that we just instantiated. There's a part of me that thinks that this should be done in the constructor via something like in the octree constructor self.triangles equals mesh.triangles, but this is likely going to just not really help us out at all with some of the things that we want to do with the octree in the future. So instead, self.accelerator is going triangles is going to be equal to triangle array. So this is just going to contain a reference to the very same triangle array that was passed into the mesh constructor. If you're following Gabor Zauer's game physics cookbook, which, as I've cited on numerous occasions, is where I am getting a lot of this information from. He's doing a little bit more when it comes to octrees in terms of like C++ pointer spam, but since we are using GML, we have the luxury of not dealing with C++ pointer spam, which I think most people can agree will generally make our lives easier all around. So if I were to run the game now, nothing would happen. We haven't really done much. If I were to instantiate a triangle mesh, nothing is going to happen. You will notice, by the way, one of the off-screen changes that I made is that when you construct a test mesh, the process is timed, and it pops out in the console how long that process took. I want you to pay attention to that, because while right now it is pretty quick to instantiate a triangle mesh, once we start to optimize this a little bit, it is going to take quite a bit longer. So first, before I do anything else, let me make another commit. Let me say this is going to be create an octree. If I were to go back over here, and I think I'm going to split this into two panes right now so that I can... No! Workspaces, help. What are you doing? So that I can see both the collision mesh constructor and the octree constructor, because I'm going to be writing some code in both of them for the rest of this video. So the main thing that I'm going to need the octree to do is be able to subdivide itself. So I'm going to define a method. We're going to call this static split. This is going to be a function which is going to take a single parameter, which is going to be depth. Contrary to what the syntax highlighting would have you believe, this is not going to be depth related to the GameMaker room editor. This is going to be a recursive function, and this is why I said I was strongly considering making a video about recursion before I did this, but I have not, at least not yet, so bear with me. First, I'm going to check for a base case. This is going to be if depth equals 0. I'm just going to say return. Anyway, the depth value, this is going to control the number of subdivisions inside an octree. I did mention that you can do this recursively as many times as you want. We are going to, when we initially split an octree, we are going to do it, for example, we're going to tell it to split itself into 3 levels. Depth refers to the level. Each time we are going to subtract 1 when we go down a level. And if depth hits 0, then that's going to be our signal to stop. Next, and these next two things are just going to be little safety checks. If array length self.triangles equals 0. So if there happen to be no triangles in part of an octree, when we try to split it, we are going to not do anything. We are simply going to return. And if self.children is not equal to undefined, we are also going to return. We're going to be assigning a value to self.children in this method, and if you have already split an octree, we will not be allowed to do it again, because that will cause some pandemonium, which we do not want. So next, let's define a few local variables. One of our center is going to be self.bounds.position. This is the center point of our axis line bounding box, representing the bounds of our octree. Next, var sides is going to be self.bounds.half extents. These two values are essentially the the two important pieces of information that make up an access line bounding box. I'm saving them to local variables now because we're going to be referring to them quite often. But I also want one more thing, which is to divide self.bounds.halfExtents by 2. We're going to be using this information to construct the inner octrees for each split of the octree, and we want the side length of the inner octrees to be half of the originals. You can divide it by 2 if you're one of those people. You know who you are. You can also multiply by 0.5. It doesn't matter. So let's create the inner octrees. Those are going to live in an array which is going to be contained in the self.children value. So I can define an array for this. You can use an array literal. This is going to be the second block of very tedious and repetitive code that I'm going to be typing out in this video. If you want to just copy and paste from my GitHub repository into your own project, I would not blame you. First is going to be new call octree. Call octree takes a bound, which is an access line bounding box, so we're going to say new ab, new call ab. The position, the central position of this is going to be center.add, so this is going to be the central vector 3, and we're going to add some values to it. We're going to add approximately half of the side lengths of the original bounding box. So we can say, and unfortunately we can't just make this as easy as center.add sides or whatever, because the different octrees that are going to be in the different subdivisions are all going to be slightly different from each other. So I'm going to need to say new vector 3. And this is going to contain a few things. For example, negative sides.x. I'm going to leave a couple spaces so that all my code lines up with all my other lines of code. Sides.y, negative sides.z. Let's see, that's the vector 3. Close parentheses again, that's the add method. The half extents are going to just be sides. And the call octree constructor takes one more parameter, and that is going to be self.mesh. Okay, that is one of the 8 subdivisions that we need for the octree. We need 8 more of these. 2, 3, 4, 5, 6, 7, 8. So again, this is going to be very tedious. I am going to refer carefully to my notes. In fact, I think I'm going to just copy and paste out of my notes. What happened? GameMaker? Anyway, copy and paste fails aside, this is what the code looks like now. You can see that each of the inner subdivisions now contains an octree of its own, offset from the center of the original octree by half of the bounds in 8 different directions. So one to the left, one to the top, one to the front left, so on and so forth. Again, if you want to just copy and paste this code from my GitHub repository, I would not blame you. If you want a quick sanity check, the signs on the side XYZ going down goes minus, plus, minus, plus, minus, plus, minus, plus. On the Y, it's 4 positive sides.y and then 4 negative sides.y. On the Z, it is minus, minus, plus, plus, minus, minus, plus, plus. And all the other lines are more or less identical. They all take the same mesh as their inner mesh. They all take a collision ab into the octree constructor. Okay, so now that we've initialized all of the inner octrees, we need to actually populate them with triangles. And to do that, we can say for var I equals 0, I is less than 8, I plus plus. If you do not wish to have a free-floating magic number in here, you can use, instead of 8, array length self.children if you wish. I do not particularly think it matters in this case. It's not like you're ever going to have anything other than 8 in an octree subdivision.
Hey.
We are going to deal with each of these inner octrees in turn. I'm going to say our tree is going to be self.children stored at index I. And then for each of the triangles stored inside the octree that we're splitting, so for var j equals 0, j is less than array length self.triangles j++. First, we're going to check whether each of these triangles in our main octree that we're splitting is located within the bounds of each of these subdivisions. We can say if tree.bounds.check triangle self.triangles index j. And since the bounding box is simply a collision ab, since the bounding box is simply a collision object, it also has access to each one of the collision checking functions within it, collision checking methods within it. So we can say if the tree.bounds.check triangle of each triangle in the octree, then we can array push tree.triangles, and the triangle is going to be the data that we're going to push onto the triangle array is just going to be a reference to that same triangle. If constantly using the array push function here bothers you, hopefully soon it will bother you less, because Yo-Yo Games is eventually going to optimize the array push function to make it much faster. You can also essentially do 2 passes over the triangles array, one to figure out which triangles are inside it, and another to actually populate it with each triangle. And then you can initialize the triangles array with something like this, and then you can do another loop over to actually populate it with the values. But honestly, since that's going to involve double the number of triangle collision checks, it's probably not going to actually be that much faster. Anyway, this code is going to run for each of these subtrees, and then once you have populated each of these subtrees with the triangles that are contained within them, we can say tree.split. We can recursively call the tree.split method with depth -1 as the depth value. If you do not include the -1, you will have an infinite recursion on your hands. Your game will never start. If for whatever reason you find your game behaving strangely, if you find your game hanging or getting stuck in an infinite loop otherwise, you might want to check to make sure that your i's and j's are in the correct places, that you're using like the correct loop counters in both of the loops and that kind of thing, and that you're not using the wrong one. That's another cause for infinite loops. And is there anything else? So once you split a node, we don't really have a need for our own triangle array. If you want, you are free to just set the original triangle array to empty array or something like that, or you can set it to undefined. But it's there's no real harm in just leaving it there. Again, in Game Physics Cookbook, which is targeting C++, which does absolutely nothing to manage your memory for you, Gabor Sauer would have you manually deleting your original triangle array at this point, but since GameMaker does a lot of things for us, we do not need to worry about that. Another thing that you do not need to worry about, that you will find in Game Physics Cookbook, by the way, is a function to delete an octree. But since there are no dynamic structures in here, no anything that needs to be manually deleted, this is just structs and arrays, we do not have to worry about that. So now if I run the game should run and it shouldn't crash or anything like that. If I were to hit the M key, and construct a triangle mesh, nothing is actually going to happen because I'm not actually doing any splitting of the triangle mesh in the first place. So let me say self.accelerator.split, and I'm going to go with 3 levels deep. This is in the call mesh constructor right after the original octree has been created. Let me try running the game again. We're going to see that the game is gonna take a couple seconds, and then after about 2,000 milliseconds or 2 seconds and change, we're going to have a tree popping up. And how long did it take to instantiate a mesh shape the first time? About 3 milliseconds, and now it's almost 1,000 times that. This is because we are doing an awful lot of computation up front to sort each of the triangles in the collision mesh into an octree. This is fairly computationally expensive up front, but as we're going to see later, it is going to speed up collision checks of all types against the octree by a solid amount. So that's the last thing that I wanted to do in this video. I am going to commit this change. We can commit split an octree into subtrees. I'm going to add just a little tiny bit more debug code to draw the bounds of not only the original bounding box of a triangle mesh, but also the bounding box of every octree inside it. So let me find my test code. That would be self.data.accelerator, and we're going to call debug draw on that. So let me start that again. Let me run the game again. Let me instantiate a mesh again. That's going to take about 2 seconds. If I were to hit the tab key, we can see that there's a little more going on there. If I were to zoom in and hit the tab key, you can see that we have subdivided the original bounding box into many inner bounding boxes. You can also see that the denser parts of the tree have more subdivisions. So the outsides of the tree that do not have any triangles in them, we have not bothered to split these some of these outer blocks further. But for example, the top of the tree with all the leaves, there's a lot of triangles in this space. We have gone all 3 levels deep in here. If you wanted to, you could split the tree. Where are we? You could split the tree further. You could split it to, for example, 4 levels. In this case, it's not really going to make a difference because each and every one of the triangles in this tree object are large enough that by 4 levels deep, it's probably going to occupy more than one subdivision in the octree anyway, and it doesn't really. It's just really going to be a waste of time. You can see that it is taking longer to draw this debug bounding box because there's so much more of it now. You can see out in the console that it took about twice as long to subdivide it at 4 levels down than it did at 3 levels down. On the other hand, if I were to only split 2 levels, and that might honestly be enough for this tree model, but if I only split 3 levels down, it is going to be much faster to do, but the tree itself is not going to be nearly as dense. Okay, that's a visualization. So I'm going to commit this change. And that's going to do it for me for today. Next time, we're going to actually use this data structure to do faster collision checks against each of the shapes that we previously defined. And also, hopefully I'll have time for this. Hopefully it won't run as long as this one did. We'll also do the raise and line collision checks against the octree. That should be a fun time. So, my name is Michael. I like wizards and dragons and making games. I have a Patreon, so if you want to contribute towards these videos being made, check for links to that in all the usual places. You can see some fun things like your name in the credits, or hearing a verbal shout out of yourself at the end, or about once a month I post a preview of my future plans. And if you wanted to pledge, I would definitely appreciate it. Otherwise, if you want the code for this, look for the GitHub repository down in the video description. Hopefully I will actually remember to post it this time, because in the last couple of videos I forgot about that for quite a while. But like I said, some of this is fairly repetitive, and if you wanted to copy and paste out into your own project, I would not blame you. Otherwise, I try to post 1 or 2 game dev videos a week, so if you're interested in any of that, feel free to subscribe. I hope you all found this useful, and I will see you all later. By the way, since this is a very cool visualization, if you're wondering what this looks like with a larger model, and this may take a few seconds, because it's a rather big file, I want to say this is about 5 times as many vertices as the Kenny tree. Here is the Going Merry, and here it is subdivided into an octree. I think it looks nice. Special thanks to Army Armbuster, Edward Holt, Emily Koyo, GameMaker, Gunnar Clovis, Posho, Sindra Larson, Squarecrow, The Nothing Happened, Tusk, and Zenjamin for supporting these videos. If you want to see your name in the credits or hear yourself shouted out at the end, head on over to the Patreon page down in the video description to join the fun.